So let's go ahead and start with stability of structures, just in a general sense. And I want to just introduce this concept by bringing in a little, let's think of this as a board. So there's a free floating board here. And of course, every engineer in the room would say, hey, this board is just floating in space. This doesn't work. I have to prevent a few things. I have to prevent this 2D system from falling down. I have to prevent it from moving left and right. And I have to prevent it from rotating. So those three things have to be prevented. And you have done this in the past already when we talked about simply supported beams and cantilever beams. So let me take the example of the simply supported beam. If I would just show this here, I would have a support block here and then maybe a support block here. And the layman would say, hey, the system is already stable. It's not going anywhere. But the engineer knows better that this system is not stable. Although the system cannot fall down, and let's pretend it also cannot move up here because it's anchored to the ground through these blocks. And although the system cannot rotate anymore, this system is technically free to move left and right. And you have prevented this in the past by using a pin. So let me, for example, put the pin here on the right side. So there's something that actually anchors this. And just to be sure that we understand that it's anchored, I also introduced these little connector pieces here that prevent this from going up and down. And if I were to draw this as an engineer would, then we would have a system that looks probably something like this. There's the pin on the left side and then the roller here on the right side. And so far so good. You have seen this before. You have dealt with this. And you hopefully already put it together that the reason this is stable now is because we're meeting some conditions, right? So we have the sum of the forces in X can be equal to 0. We have the sum of the forces in Y is equal to 0. And we have the sum of the moments about the Z-axis being equal to 0. Because keep in mind, we're talking about 2D systems here. And only for 2D systems, a system would be stable if these three conditions are met. In fact, we can give this a headline and call this hashtag stable, right? I hear it's trending today. So stable is a system that allows these three conditions to be true. But now you may say, hey, this is true for this system, but I can do other things to make a system stable too. And you're absolutely right. So let's take this to the next level and let's draw the same system again. So I take the very same beam here and I apply the very same support reactions to it. So let's say I have a system here, and then I have another support here, and one support here, and I'm not drawing these blue connectors anymore. But what I can do now is I can add another support. So let's say I'm adding another support right here. And of course, the system now is actually more stable, right? So this system is more stable than this, and this is still true. So engineers need to understand the difference between this system and this system. If we were to draw this like engineers do, then of course the system would look very similar to what you have seen before, but with one added support reaction here. And be careful, this support here sits underneath the beam. So it's not a circle through, right? So please understand that this here sits only underneath the beam and not in the beam. That makes a difference, as you will see later throughout the lecture. But now we can still fulfill these conditions, but we have one support reaction more. And as you will see in a little bit, you can actually not solve this system with the methods that we have. And maybe you can already guess why that is. But let's continue our thinking before I tell you why that is. So I can, of course, take the very same system again and make it even more stable. So let's do that. So I have a system that now looks like this, which is exactly the same as we had before. But I will make it even more stable by adding yet another support here. And that system, of course, is even different from the one before. So now the system would look something like this. And that, of course, makes the system more stable. if you want to think about this from a standpoint of deflection, you probably understand that this system here deflects the most if you put a force on it. So let's actually pretend we have a force sitting somewhere on there. So this force, of course, would deflect this system very differently than this system, for example, or this system. So this would just start to bow down, whereas this one here would bow down here, and then here you would actually have an uplift, if you will, or like an upwards bending. We talk about bending much later, but you understand that this support here changes how this entire structural system responds. And the same is true here. So this support here now adds some different behavior. And so engineers really have to define that, and engineers have to also know, hey, how do we think about this in terms of stability? Let me give you one other extreme, of course, just to see the other side of the equation, or the other portion that we talk about here. So we talk about stability, and of course I can have a non-stable system. So for example, let's say I have a system that looks like this. That would be not stable at all. So that is it, right? And so this would be unstable or understable or whatever you want to call it. In fact, engineers would probably call this system kinetic. It's a kinetic system, right? So this would be kinetic just because it can move. While it cannot fall down here and it cannot move left and right here, it could totally rotate downwards. So the system would actually be allowed to rotate here, and therefore it's a kinetic system. Whereas the other ones are all stable, but they are all stable in a different way. So engineers need a way to define that. And the way engineers do that is by calling this statically determinants. So this is a statically determinant system. Let's write that on the side. So this is statically determinant. Whereas the other systems are actually statically indeterminate, right? So statically indeterminate. And the problem is that the second one here is also statically indeterminate. And of course, you already understand that it's not good enough to differentiate only between this and this one and have these two say the same thing, if you will. So this is actually what I would call stable or overstable by one, right? So let's put this in layman terms here on the right side maybe. So this is overstable one time, whereas this here is overstable two times. And again, this is not what an engineer would say. An engineer would actually say, hey, this is statically indeterminate to the first degree or to the second degree. So the first system here is actually statically indeterminate to the first degree. And the second one then here would be to the second degree. So in other words, you count the overstability and you make sure that you have this condition taken care of first, or these three conditions are taken care of, and then everything in addition to that is an overstability. And engineers don't call that overstability, they call that statically indeterminacy. So let's draw one last system just so that we understand how this actually applies. So I'm going to draw a little bit of a longer beam here, and I'm going to add some random supports to that just to play the game further. So for example, I have a support here now, which again, keep in mind, it shows that it's up and down and left and right is what these are. And maybe I'll put one here, and put one here. And I encourage you now to go ahead and pause the video and think about how many times the system is overstable and how you would draw it as a rigid body, as it is here in this column the case. So go ahead and draw that. I will do that for you in a second, and I will also define how many times it's statically indeterminate. But maybe you can already do that on your own. And of course you did. So it is no surprise when I now show you that here we actually have, let's say, a pin, right? And then on the other side we have a pin as well. And don't be fooled by that pin. That of course already, this system here would already be overstable because we have one more support reaction than we need. But to copy what we have on the left side, it would look something like this, which I need another one here. And then I need another one right here. And by the way, if you are confused about this block here and then this symbol, please keep in mind that the symbol, the pin on the right, is nothing else than a system that looks like this. So I could have a roller here and a roller here. That would be equivalent to a pin. So two rollers here, they prevent left and right and up and down. This would be equivalent to a pin here. But now count your support reactions for now at least. So we have 1, 2, 3, let's say, and that would already be a stable system. But now I have 1, 2, 3, 4 additional support reactions, and so therefore this system would be statically indeterminate to the 4th degree, right? So this system here on the bottom is statically indeterminate to the 4th degree. Why? Because I already fulfill my equations here and my conditions, but I have 4 additional support reactions. One here, one here, one here, and then one of the other ones on the outside, if you will. You could also do it differently, by the way, so let me use a different color for that. So I could, for example, say, hey, I have 1, 2, and 3, and then everything else is redundant or makes it more stable. It's not redundant, it actually makes it more stable. So everything that has not a green line to it right now, that would also be overstabilizing the system. And now I invite you to think about this. Why were you able to solve support reactions for systems like these? You have done this already in your homework, but why would you not be able to solve these systems? And the answer is actually on this page here right now. And of course, I'm not telling you too much if I say that this is the real reason here. So the reason you can solve these simply supported beams so far only and not these systems below is because you have 3 equations, right? Or 3 conditions. And when you want to solve 3 equations, you can solve to a maximum for 3 unknowns. And that's exactly what you have. You have 1 unknown here, 1 unknown here, and 1 unknown here. So if you have any more unknown, these conditions are not enough anymore to solve the system. And so if you have more than 3 unknowns, you need initial conditions or boundary conditions, depending on what system you would solve for. And that technically goes beyond the purpose of this class, but since we're talking about stability here, let's quickly conceptually talk about how you would analyze this. So, for example, if I have a force acting on this beam here as well, then I could treat it like this beam above here first, and I could calculate what the deflection at this location here would be. So for example, here's the support, so I want to calculate what would be the downwards deflection. And again, we can only do this conceptually because in this class we have not discussed yet how to calculate deflection. It's way beyond the purpose of this class right now. But if you were able to calculate how much this deflects downwards, if the support is not there, then you can use the boundary condition of the support, which says, hey, the deflection here must go back to 0 because the support does not allow this to go down, so that you can actually calculate how strong the support has to be to bring it back into the 0 position. And you can do this multiple times. This is conceptually how that would work. But what's important for us to understand is that we so far can only solve 3 support reactions because we have these 3 equilibrium equations. But there's a system or a type of systems that actually remain statically determinate, although they have more than 1, 2, 3 support reactions. So today we will see some systems that have maybe 4 or 5 support reactions, but they remain statically determinate and they are not statically indeterminate. But before we move on to those problems, let me give you one word of caution about something that you sometimes read in the literature. Some people in the literature say, hey, if you want to find out how many times it's statically indeterminate, all you have to do is count support reactions and then subtract 3. So the logic in the literature is, hey, this allows you to find 3 unknowns and then you count. And this works for all the systems that you have seen here, right? So for example, if I count here, I have 1, 2, 3, 4, 5. And then I subtract 3, so that leaves me with 2 unknowns. And that's true and that works. But there are sometimes systems that have more than 3 support reactions, but they are completely useless. So for example, if I were to draw a system here that looks like this, and I have a support here, and a support here, a support here, and a support here, then you would probably agree with me that we have 1, 2, 3, 4 support reactions. And if I were to count this and subtract 3, then I have statically indeterminants of 1. But that is completely useless because the system here is also kinetic, right? So this is also a kinetic system. And therefore, I cannot use this as a structural system. And so I always caution students to not use any formulas. So for example, the formula that they list in the literature, of course, is n minus 3. But sometimes that doesn't work. And there are other systems where that doesn't work, which I will not allude on to further here because we haven't covered some other topics. But I just would caution you to not use simple formulas. It's better to have a physical understanding of the system. And talking about physical understanding of the system, let's actually move on to the statically determinate base systems.